In fact, this whole chapter is dirt and rocks and volcanoes. It's I know it's hard. I know it's real hard because it's hard for me. I'm not particularly interested in teaching this stuff. But I gotta tell you, there's so much of this information on the ACE exam. A little bit less so for the AP exam, but you've got to have this terminology. I'd like to add some music. But what kind of music's got dirt in it? I was looking for the theme song to the movie Joe Dirt. Nothing. There used to be a band in the 70s, the Nitty Gritty Dirt Band. So I could play a couple of their songs, but it doesn't have dirt in it. And of course, this is really about soil, not dirt. But to me, it's all the same. Anyway, just because I'm not all that interested in teaching this doesn't mean you can't pay attention. You've got to. Because your success on the AP exam and the ACE exam counts on you knowing this information. I am not going to be the one to sell you short and not prepare you for the big exam, because that's my job. So I'm going to give this the same effort I give all the other topics. Here goes. Let's talk about soil. Dirt. Alright, so here it is. Soil formation. This is the soil cycle, if you will. We had the tectonic plate cycle. We had the rock cycle. That's why this is number 3. This is the soil cycle. And the soil formation links rocks, dirt, to the biosphere. Because guess what? Soil is full of organic material. And that's one of the key roles of soil, is the fact that it recycles organic material, nutrients, back into the environment. Of course, also soil is a key component in the formation of, or the ability of plants to grow, because of the root system and all of the different nutrients that are in it. So here are the reasons we have to care about soil. Filters water. It's a habitat for lots of the decomposers and other organisms that break down nutrients. It's a medium for plant growth. So that makes soil a key in the biosphere. 5 factors in the formation of soil. First of all, there's the parent material. We're more on that in the next slide, because we're going to talk about how soil is formed. But another key thing for soil formation is what kind of climate is there. It's very important. There's a reason why we feed the world. Our climate is perfect for the formation of good, rich soil in the breadbasket of America, right there in the middle states. And so climate is key. Places where the climate is not so good, not so hospitable, the soil also is not very good for growing. Topography is the lay of the land. What kind of hills and valleys and so forth is there? So the formation of soils depends on topography. If there's a gentle slope somewhere, the soil formation will be different than in a flatland area or in a steep slope. The number of organisms that are in the ecosystem is important in the formation of soil, because as we'll see, these organisms don't just churn up the soil and add oxygen and air to it, but also these organisms decompose and add nutrients to the soil. And time. And this is why we worry about soil as a resource, because it takes a lot of time for soil to come back. And because of that, we have to worry about soil being a non-renewable resource. Now, if you were asked, is soil a renewable or a non-renewable, we put it in the category of renewable. Soil is a renewable resource because it can come back in your lifetime. But certainly time is a key factor also in the formation of soil. Here's how soil forms. It is dirt. It starts with rock. And this bottom layer of soil is called the parent rock. And that parent rock, which is down deeper in the soil here, that parent rock breaks up and weathers because of all those things we talked about previously. It can be wind, it can be rain, it can be physical, it can be chemical. Whatever it is, this parent rock is weathered and breaks down, and because there's always new rock forming deeper, remember the rock cycle? From the magma, it pushes this rock layer upward. And so as it gets pushed upward, organic material accumulates as plants and other organisms die. So then we have richer amounts of soil, again over time. And we're going to talk about what these layers are in a moment. But as time goes on, this immature soil, this bedrock bottom, gets broken up into tiny little pieces. That enables plants to grow there. And then the plants die and we get good organic material in the soil. Mature soil then has been around for thousands and thousands of years. There's greater amounts of organic material in what's called mature soil. Immature soil basically is broken up rock. Young soil is broken up rock but with some dirt on top because of decaying and dead materials that were plants. And then mature soil is when you've got great big trees, lots of root systems and things grow in the mature soil. Alright, this is a memorization time, I'm afraid, but it gets asked all the time. This is one of those diagrams that's a big, huge thing when it comes to environmental science. And that big, huge thing is this diagram of the layers of soil. The layers of soil are called horizons. Don't ask me why. But they are these different layers that we have of soil are called horizons. The top layer of soil isn't A, it's O. Who came up with this idea? So the O horizon is the very, very top horizon. And basically, it's the organic matter that's on the very, very top. And you can see it doesn't go down very deep. In fact, root systems go down way below the O horizon. The O horizon is just the top layer of organic matter. As far as I'm concerned, it's really not part of the dirt. It's just right there on top. The next layer is called the A, and of course then we have the B, and then we have the C. You should be able to know, or remember, that the A horizon is also known as topsoil. It's the zone of overlying organic material, and it's mixed in with lots of dirt from down below. The A horizon is topsoil. The B horizon, you can tell, is much deeper. It goes about 0.7 meters. And you all know what a meter stick length is. It's about a yard, so this gives you an idea of the depth that we're talking about here. Down to about 1 meter is called the B horizon. It's also known as subsoil. And the reason subsoil matters is because this is where metals and nutrients accumulate. So this B section, the B horizon, is where root systems want to be able to reach down to get to. Those roots are seeking the accumulation of metals and nutrients that happen at the B horizon. Very little organic matter down here. And then the C horizon is known as subsoil also, but it is down a ways. Now we're talking about 1.5 meters to 2 meters down. This part of the soil, hey, you can go in your backyard and you can dig down to the C horizon. It's the least weathered portion of the soil profile. It's similar to the parent material. Not a lot of nutrients down here. Roots don't usually try to get down to this level. And the reason for that is simple. There's no metals and there's no nutrients here in the C horizon. It's also known as a parent material. C horizon, parent material. Alright, so memorize this diagram. It's on page 223 in your book. You need to memorize those horizons and match up the characteristics for each one. Alright, when we talk about soil, we talk about its physical and chemical properties. Two very different things, and we'll start with the physical properties of soil. One of the most important physical properties of soil is what is it made up of? That's called its texture. And the texture of soil is basically three different things: the amount of silt, the amount of sand, and the amount of clay. Now you're familiar with sand and clay, and I have to tell you that silt is basically a combination of the two, of sand and clay. You're familiar with sand, of course, because you go to the beach. The beach is full of sand. Sand has large granules. Take a look at this picture here. Sand has large granules, and they're very have lots of different shapes and sizes to them if you magnify them. This is a picture of different soil granules. I'm sorry, sand granules. So sand has lots of different shapes and sizes to it. As a result, it's not very uniform. The sizes of the particles are quite large, and even though this picture shows them as round, the fact is if you took an individual grain of sand and looked at it under a microscope, it would have these very, very unusual shapes and sizes. That makes it hard to squeeze and compact. That also makes it hard to hold water. Now clay is sort of the opposite of the sand, as you can tell here from this diagram. Sand particles are tiny and they're very uniform. If you take a handful of clay and squeeze it, it stays squeezed, doesn't it? Because each individual granule of clay is so uniform and so tiny and so alike, it holds that shape. Sand isn't like that. Grab a handful of sand and squeeze it. Those granules still just fall through your hands because each individual granule is not uniform, so it doesn't stay together. They're so unique and different that they just fall apart in your hand. This diagram is a famous environmental science diagram. Just like the demographic transition diagram, the predator-prey diagram that we've had before, this is another one of those very, very famous environmental diagrams. And what it does is it enables you to find out what percent of each of these three textures a sample of soil has. And you can see here we've got percentage of clay, we've got percentage of silt, and we've got percentage of sand. And in your diagram, it will always look like this. What you do is you find what the percent of one of these is, and it enables you to look up the other two. Please note when you use this diagram, and we will go over this in class so that we can practice playing with it. When you use this diagram, that the answer that you come up with, if I tell you to go here for instance and find out what is the different textures, you'd be able to do so. When you find those percentages, as in this example here, when you find those percentages, they add up to be 100. If you're ever asked to come up with the percent of sand, silt, and clay for a particular sample, just make sure it always adds up to be 100, because that has to happen in order for you to use this diagram correctly. In class tomorrow, we'll play around with the usage of this particular diagram. What's instructive about this, obviously, if we've got, for instance, on this axis we have percentage of clay, obviously then the higher percents of clay are going to be mostly a clay-like substance. Very little silt, and there will be very little sand. And likewise, when we look at percentage of silt, we have silt here, and so where we've got the highest amounts of silt, of course that's going to be called silt. Now another term that's on this diagram that you need to know is loam. Loam is the perfect soil. Loam is, you can see it here in the dark purple, loam is the best soil for growing crops because it is a percentage of each of the three textures. Not too much sand, not too much silt, not too much clay. Why does that matter? Well, you know darn well in your own experience just living where you live, clay is not a good soil to grow crops in. The reason for that is clay holds water. So the root systems of plants, they don't get to breathe much and they become what we call waterlogged as a result of too much water in the clay area. Sand has its problems, of course, because water just goes right through sand. You know, have you ever tried to fill up a hole that you dug when you were down at the beach as a little kid? You ran to the water, you grabbed your little bucket, you filled it with water, you came back and poured it in the hole. Then you went back and filled up your bucket again, but by the time you came back, the water that you poured in the first time was all gone. Water flows through sand. So sand's not good for plants because they don't get enough water that way. The perfect soil for growing crops is called loam. On a test question you might be asked, what kind of soil is here? Let's pick one here. Let's choose this place right here. First of all, always go straight across with the clay. So that's what you'll do. You'll go straight across here and you'll say, all right, that's 50% clay. Now the next thing you do is you follow the line towards the silt. And the rule of thumb is always go to the lowest line. You can see here you could go across here to 50, but that would be a mistake. You want to go up here to the line that goes the lowest. That's 20. All right, so we've got 50% clay, 20% silt, and you know then that the percent sand is going to be 30. And again, same idea. When you've got more than one line going to the space that you're trying to analyze, you go to the lowest line. And in this case, if you went this way and followed that line, you'd be up in the 80s. That's not right. So you follow this line here, it's down to 30, and sure enough, that's exactly what you'd expect. 50, 30, and 20, that's the 100%. All right, so that's how you use the diagram. I said we'll have more practice with that later. The other properties of soil, they're still physical. They have to do with porosity, as was mentioned in the video. You've known this probably. I mean, have you ever made a bowl or a dish or something out of clay, like when you were a little kid? Clay holds water well, and that is called porosity. How porous is it? How many air holes are there? You know, think of pores like pores in your skin. How many air holes are there in between the granules? Well, when it comes to clay, there are not many pores in between the individual tiny little granules. Because remember, these clay granules are tiny and they're very uniform in shape, so they compact, they squeeze together. So clay has a low porosity, not many holes in it. Sand, of course, will be the opposite of that. Sand, as you can see from this diagram down here, sand has many holes in it because they have lots of different shapes and sizes of granules. So sand is very porous, and that means it will not hold water very well. And that's been your experience. Silt is in between. Silt's in between. Not real porous, but not terrible like sand is. And this picture here kind of just shows you that small granules, very uniform in shape, means low permeability. Not much water can get through. Sand, all the water gets through. It has high permeability. Chemical properties are the other things we talk about when it comes to soil. Something called nutrient holding capacity. I believe on the AP exam this is what it's called, nutrient holding capacity. But there's another more scientific name for it. It's called CEC, the cation exchange capacity. Well, what's that mean? You might realize that when you go to the store and buy fertilizers, you are usually buying something with a positive charge, a cation, calcium +2, magnesium +2, sodium is +1, as is potassium. These are cations because they are positively charged ions. They're also usually the base part in an acid-base reaction. So cation exchange is the ability of the soil to hold and to allow to react these different cations. In addition to cation exchange capacity, and again, this should make sense to you, good soil is going to have good CEC. It's going to be able to hold these different nutrients that are in the soil. That's why it used to be called nutrient holding capacity. The chemical properties of soil also include how acidic or basic is the soil. Acidic soils are not good. And again, in the food chapter, we'll talk about soil acidification. The things that happen to soil that lower its pH and make it very difficult for plants to grow. Aluminum ions and hydrogen ions are part of the process that tends to add to soil's acidity. And then there's something called base saturation, and just as the term indicates, it's the proportion of bases to acids. You always want there to be a little bit higher when it comes to bases than you do when it comes to acids. The biological properties of soil are all about the living things, obviously, biological properties, living things, and we can talk about decomposers on the surface, things that just slither and slide on top. We can talk about excrement that's provided by larger animals. That's part of the biological properties of soil. We can talk about worms and other organisms that tend to churn and break up soil. This is a very, very good and important function that earthworms play in soil. If you want to know how healthy your soil is, if you've got a lot of worms, that's a good thing, because those worms are living. And you know how worms eat. They're continually ingesting dirt, soil. They're continually ingesting it in the front end, and their intestinal system, their digestive system, which includes a gizzard and a crop, break down that soil, get all the nutrients out of it, and then what comes out the other end of the earthworm is just the soil without the nutrients. But this churning and turning and moving of the soil, very important for the health of the soil. And of course you've got microscopic organisms like protozoa and bacteria also in your soil. And the occasional burrowing creature, mole, armadillo, things like that, that add to the biological properties of soil. All right, what are the things that we're concerned about when it comes to soil? Let's just cover them real briefly. First of all, topsoil loss. Obviously that can be from wind, it can be from rain, erosion, but loss of topsoil means you don't have that basic organic layer. Remember, the A horizon is the topsoil, and that A horizon has living material or organic material that was once living. And topsoil can be lost because of overuse. It can be lost simply from deforestation. Compaction is when we use the same soil over and over and over again, and without any worms sort of breaking up and chewing up the soil, making it break apart a little bit, you have compaction. That's when the soil is flattened down. It almost acts like clay, even if it's not composed of clay. That soil is so compacted, it holds water, water doesn't get through. We have depletion of nutrients. This can happen in a wide variety of situations, A lot of times depletion of soil nutrients happens just because of overplanting. If you plant the same farmland year after year after year and don't give it a chance to kind of rebound and restore its nutrients, that same plant over and over again that requires the same types of nutrients will basically take all the nutrients out of that soil, and now it won't be very good for that particular type of plant. This is why farmers oftentimes rotate their crops. They use crops that have different nutrient needs at different times, so that gives soil nutrients a chance to rebound. And of course, we all have the ability to pollute our soil. Farmers use a great deal of pesticides to keep bugs and other critters away from their crops, and those nasty chemicals, after all, sides means death, homicide, suicide. So this is death to pests. Well, if it's a nasty enough chemical to kill a bug, it's a nasty chemical. It's not good for any other organisms either. So overusage of pesticides means that soil gets really bad, and it can become so bad that it's not even good for plants anymore. That is all I needed to cover on soils, and boy am I glad that's done. We will do the last section of this chapter, which is about mining, and there are some very important environmental problems associated with mining. We will hit them in the last video for this chapter. Adios!